All right, let's talk about transformations. Over the next 2 days, we'll be homework 6 and homework 7 deal with transformations. And again, like I've said a few times already, my hope is that we're going to take this to the next level with you, right? I know you already know some of the things we're going to say today, but I'd like to throw functions at you that you've never seen. I'd like to say some things and reveal some things that I hope will take you a little deeper. The first thing we should say something about is rigid transformations. And a rigid transformation, this is a loose way to say it, is one that leaves the size and shape unchanged of your graph. And if you've used that language before, especially even in geometry, you probably talk about rigid motions a lot. The first rigid motion we'll talk about is translation. What are the other two? Yeah, rotation and reflection, I hear from the peanut gallery. Good job. And said slightly more precisely, another thing to say about rigid motion is that it's a transformation that leaves all distances preserved and all angles preserved. It's actually a pretty deep conversation to have. If you want to come by sometime, we'll talk about transformations. Okay, so again, I'm just going to throw these up here. These are copied directly from the book. Today I'm going to have like a bunch of language on these slides. I'll leave it up to you to decide how much you want to write down. It's really literally just copied right from the book, and you also know that I provide these PowerPoints and videos for your consumption after these things happen. So I think these are familiar to you. Let me say something about horizontal translations too. Both of these are both vertical and horizontal translations are extremely familiar to you. At this point, I would assume that in Algebra 2, you've done them quite a bit, and you're comfortable with them. And through lots of examples and observation, it's like science to you. It seems to be the case that these hold. Can you create some reasoning around why they work, though? And the answer is, I think, yes, pretty quickly on vertical translations. For vertical translations, not only does this is something you know, it's also something I think you can probably thoroughly explain. And it goes like this, right? It's that if we add a number, it's the same as the old graph, isn't it? The only thing different is the y values are all c units higher or lower. And so visually, of course, it corresponds to a vertical translation up or down. That makes just like good sense. But I think your reasoning around horizontal translations maybe not all there yet. The reason I usually hear, the explanation I usually hear from people is, well, I do what I think makes sense. I think about what makes sense, and then I do the opposite of that, right? Am I right? That like some of you are, like that's where you're at with your reasoning on that? And I think we should never settle for that in mathematics. Like mathematics is a sense-making discipline, and so never should we have as our explanation, I'll think about what makes sense, and then I'll do the opposite, right? That's a terrible explanation in a discipline which claims to just always be about reasoning and sense-making. So let's try and flesh that out in a second. On the next slide, I'll try to flesh that out a little bit for you, why horizontal translations make sense. It seems so counterintuitive, doesn't it? But it isn't, and we'll make sure you understand why. And then one other comment I want to make that's somewhat new to you maybe is this notation, which I don't really care about that much, but IB does, and so I thought I'd put this on there. By A and B, we mean up top the left-right movement, and B the up-down movement, and they'll often just encapsulate all that motion into one little package. And this means if A is positive, then that's a rightward move. If A is negative, that's a leftward move. B is positive or negative, it's up or down by that amount. A quick way to kind of communicate the translation. Again, I don't necessarily prefer that way of writing it, it's just I wanted you to be familiar with it. Okay, let me see if I can explain horizontal translation. Yeah. Professional dress, business casual, right? Again, feel free to not write everything down if you want to take a picture. Okay? We good? It also will be on Edline, or what do we call it? Google Classroom. Hopefully you've been finding all these things. Okay. Again, and the reason I don't need you to take copious notes either on this, on every word, is because I think most of this, maybe with the exception of the thing I starred, is like, you're like, I know all that. So hopefully you're comfortable with the way we've written this in the f of x minus c notation, so you understand what that means. Okay. So let me see if I can explain some reasoning around why it makes sense, what we do with horizontal translations. I've started with this graph here. So this is just a parabola with some points on it. This y equals x squared. There's the table. And then the question is, how would we, for example, accomplish a rightward translation, 3 units? Well, I'll draw the picture first. Let me just show you what I intend to. This is my target here. I want to make this happen. And my first question would be, in this transformation, what doesn't change? Well, what doesn't change? I mean, take this point to this point. What hasn't changed? Yeah. Yeah, the y value. So right away in my table, if I'm making a table of this, I'm just going to say, oh, well, certainly for these 5 points, it's still the same y value. Okay. Well, what does change, and by how much? And what do we do? What does change? X, and by how much? Yeah, this point should be the point what? 1, 4. Right, good. And etc. So I'll put all those points up there now. Great. We're doing well. Now the only thing I haven't filled in here is the rule, right? So my last question is, what's the new rule? And this is the question right here that will change your life forever. Okay? Right here. What do you have to do? I'll read it. To each x value here in order for you to get the old y value. Certainly when I square 1, I do not get 4. What I need 1 to do is to act like -2, don't I? And what I need 2 to do is to act like -1. So if each of these values needs to act, what does each of these values need to do? It needs to act like the value 3 less than it, yes? So it's pretty clear to me that the rule needs to be that, okay? If each value needs to be acting like the thing 3 to its left, if you're this function and your role is to act like the thing 3 to your left, what are you in relationship to it? Well, clearly you're 3 to its right, aren't you? Okay, if you're masquerading as the thing that's 3 to your left, then you're definitely 3 units to the right of it. Okay, so all right, is that good? Okay. Life changing every day. That's my business. Okay. Try this translation here of this crazy function. You've never seen this function in your life before. Can someone, before we even launch into it though, just tell me, how do we interpret that? This is, again, just us interpreting ID notation. There's no, yeah, what do we say? This is, yeah, this means to move this graph to right and 3 down. Okay. So that's what that means. So do that. I just want to translate. That's not the interesting part of this question to me. Can you do it though? Give me a function h of t that's the same as the original function v, but moved to the right and 3 down. Go. And then do this one too if you want. Yeah. I'll give you a minute to do both of those. Yeah, right. Yes. That is my right desk. We'll try not to do anything exciting while you're going. All right. Oh, is that one? I don't know where the packet is. Someone's out. Someone in the bathroom. This person is in the bathroom.
I don't know what I'm doing. Don't trust me. I think you're the one.
All right. How are we doing out there? Come up with h of t. Think about each question separately. How do we move it 2 to the right? Just think about that individually. And then think separately about how do I also move it 3 down. Does it matter that I don't know what this graph looks like? Because I really don't. Actually, I don't. But who cares, right? I think I still know how to move it.
Yeah. Okay, so I don't know, e to the 2 minus 2 over 2 minus 2.
Are we over 20 after? Right. All right, is the chatter out there productive chatter? Are you making progress on these, both these problems? Did you do the same thing on the first one?
Pascal got because I thought it was a right now, but now
Take that half over there. All right. All right, I'm ready to hear an answer on the first one here. And let me hear from your table, Robin, actually. What'd you guys come up with? Let's come back together, if you will. Okay. Hey, listen, please, guys. Rebecca, you can go. E to the t minus 2. I'm hearing you, sorry. Over t on the bottom. Over t. Okay. Minus 3 at the outside. Yeah, okay, I like that. And just to be clear, so this is h of t. And I think I'm in agreement with you. Do you guys agree out there too? Remember, based on the language we had on the two previous slides ago, we're talking about the original function v of t minus 2 minus 3. And that language literally means a composition, doesn't it? So we plug in t minus 2 wherever we see a t. And that produces for us a horizontal shift to the right. And then when we've shifted the graph down 3, we just take the function, put parentheses around it, and tack on a minus 3 afterward, right? Good. And again, I have no idea what this graph looks like, v. You can plot it if you like. I really have no idea. I've never looked at it in my life. But I do know that h is, whatever that one looks like, it's the translation, 2 to the right and 3 down. So on this one here, I definitely know, before even starting, that there is an answer, right? Because every quadratic is some transformation of x squared, isn't it? So there's got to be some transformation here. So how do we do this? Anyone having an aha moment on this one? Does this seem familiar to you? Yeah. Oh, it is, huh? I should get Claire to do this one here. Yeah, how do you rewrite this, Claire? I forget. Or said another way, this, right? Okay. And if you can rewrite it this way, and this is the same problem as the one. Yes, that's true. Do you like how sneaky I feel like you like that? If you can, there you go. If you can write this way, then really the fun problem is the fun part of this problem is over, right? Now the game is up, isn't it? Of course now we can see. I'm not even gonna write it down. The translation 1 to the right and 6 up. All right, whatever. That was the fun part. Okay. Let's talk about reflections. Let's really think deeply about reflections, if you will. You want to reflect on? Really deeply think about it. Okay. How do we reflect a point over the x-axis? It should make sense geometrically that we take, well, what doesn't change? The x-coordinate doesn't change, but the y-coordinate, we want to make it an equal distance from the x-axis, but in the opposite direction, don't we? And then a similar conversation going to be had with reflecting over the y-axis, and I'll give you the picture if you don't feel like picturing it. There you go. It should make sense that that's the case. So what does that mean in terms of functions? How do we reflect a function? Let's start with the x-axis. How do you reflect a function over the x-axis? Go ahead, Gabriel. Yeah, again, if you want, give me like hands-on instructions, please. Well, you do what Gabe said. You take the whole thing, Gabriel, and put it in parentheses, and then put a negative out front, right? And then you walk away. That's it. That's all you do, right? Okay, that was easy. What about reflection over the y-axis? Can you give me like hands-on instructions for how to do that? Bryn wants to share. Go. Yeah, what do I do?
X, but like it has to be just X, not anything around it.
Okay. What if they're more than one x? Yeah, you replace every x with parentheses negative x, right? And like she says, make sure you get in there and replace just x. So the things they just said are what we're writing here. Yeah, does this connect? That's a good question on the second one in particular. Does this connect at all to something we've talked about before? Something to think about. Thanks for taking us there, Brent. It's strong work. Okay, again, this is something I think maybe you've thought a little bit about before, but I'm about to throw another function at you, which I don't really care to picture, but we can still do these transformations, even though we might not be visualizing the function. Afterward, you can graph it. Let's see. Let's try it with this one here. Okay? Again, I'm intentionally giving you a terrible function, which you don't immediately see in your mind. I think if you know anything from Algebra 2, if you remember all of your stuff from Algebra 2, I've gone out of my way to actually make it hard. It's a rational function, so I don't know, maybe there's some vertical asymptotes, and maybe, in fact, I think there is one, maybe. Anyway, whatever, but who cares? Can we still do a reflection over the x-axis? Absolutely. So give me that, we'll call it y1. Tell me what that'll be. And then also do over the y-axis. Call that y2, and tell me what that will be. And again, I'll give you just a minute to figure it out yourself first. And put it like this. Get both of them, share with your group as usual. More seconds till the reveal. Who am I going to get? I'll find some people. My two favorite students. You're ready with your answer, aren't you? All right, let's hear from some people out there. Hopefully you figured this out with your group. But it's okay, even if you say the wrong thing, we'll still love you. Angela, how'd you guys do? You're still having such rich conversation. Sorry. Angela, can you take number one? Go ahead, tell me what you would write. Just give me instructions. What do I write? 2 minus 3x over... Same thing, okay. All right, she's being all tricky, but it's also fine to just be like, I put a negative. I just put a negative. I just put a negative in front of the whole thing. Full credit for that too.
Okay, cool.
Thank you, Angela. Excellent work. Okay, and then Grant, what did you say for this guy here? Give me very specific instructions on how to do this here.
So replace every x with
Yeah. Okay, and then so. So what do you get in the end here? You can just give me this.
negative 3x minus 2
Okay.
over negative 4x cubed minus x squared plus 1.
Okay, and yeah, the way he got that is by doing what Bryn said a second ago, replacing very carefully every x, replacing it with a negative x, and then simplifying it. Right? So I think you've done it. Great job. By the way, some things didn't really change in this equation at all, right? This, and this, for example, didn't change at all. What if when we did this process, Brett and I, nothing changed? What would that indicate? It's what? Yeah, it's Daniel, say it like you mean it though.
It'd be even.
It's an even function, right? If when you do this, when you reflect it over the y-axis, and you're like, wait, nothing happened, well, that's an indication that your function is even, isn't it? If you take f of negative x, and you end up just with f of x, then your function was even to start with, wasn't it? Go ahead and reflect this function take x squared and reflect it over the y-axis, everybody. Oh, are you already finished? Okay, yeah, all right. Of course, there's nothing happens, yeah.
So for the second one, the denominator, that first part, why, like when you put negative and then negative x squared y, don't you just like make that a plus sign?
So what does this literally, by definition, mean? Negative x squared.
The squaring the negative x.
What does it mean to square a number, though?
Multiply by itself.
Good. So then what does this say actually? It says minus, parentheses, negative x, times negative x.
Oh, okay.
Right? So isn't that a negative x squared? There are 3 negatives there, actually. You need to see it. There are 3 negatives there. Okay. All right, well, let's at least mentioning. We're about 2 minutes to the end of the period here, so let's just mention these. I'll put these up here. We're talking about now non-rigid translations, vertical and horizontal stretches and shrinks. I'll throw this up here, but then we won't put another slide up today. This will be it. And I don't even know if we'll get a chance to actually do this problem, but you can write it down, try it. But my challenge to you would be, this should all be language that sounds somewhat familiar. Again, I just stole it directly from the book, and I know you've done vertical and horizontal stretches and shrinks before, maybe, at least a little bit in college too, I would think. And my challenge again would be for you is, can you describe, again, this one makes good sense down here. The vertical stretch and shrink, of course it's the same as my old graph. All the x coordinates are the same, the y coordinates are just multiplied by something. So that makes sense that I'm stretching or shrinking it. I think I understand that, Mr. Chase. But this one requires maybe a fancy slide. I didn't prepare a fancy slide with blue and red graphs for this one. But I think the conversation would sound almost the same if you did a graph. We talked about what it means to horizontally shrink or stretch. Because again, I think people kind of think, why is this, when I divide by 2 inside here, why does that produce a horizontal stretch by a factor of 2? And again, can you use an explanation that includes the word masquerade to explain why? Okay. You have to use the word. Yeah.
With the word pancake, masquerade, and rainbow.
Yeah. Go. That would be a challenge, but. So we'll pick up here tomorrow. I know we're running short on time here. You'll be well equipped to do homework 6. I'm just going to continue and talk more about transformation tomorrow. We'll go even deeper. Have a great day, guys. Homework 6 tonight. Homework 7 will be tomorrow night.